Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will review what was covered in week 13. So we looked at Bernoulli random variables and also the binomial distribution. So x, a random variable, is Bernoulli random variable if it can only take two values, 0 corresponding to failure and 1 corresponding to success. And we just let P be the probability of success. So, of course, probability of failure is 1 minus P. So we write this as shorthand to show that x is a Bernoulli random variable, and the expected value of such a random variable is whatever P is, whatever the probability of success is, and the variance is the two probabilities multiplied together. So let's look at an example. Let's say I roll a normal 6-sided die, and I'll define two random variables here, x and y. X is the number of 4s rolled, and y is just the number rolled. So y is not a Bernoulli random variable. The reason is y can take values 1, 2, 3, 4, 5, or 6. Bernoulli random variables can only take two values. X, on the other hand, is a Bernoulli random variable because it can only take two values. If you let x be the number of 4s rolled, we can either have x equals 0, no 4s are rolled, or x equals 1, a 4 is rolled. So this is like corresponding to success. If we want a 4 rolled, x equals 1 means we've succeeded in that, x equals 0 means we failed in that, and no 4s were rolled. So, of course, here, P would be 1 over 6. The probability you roll a 4 is 1 over 6, and the probability you do not roll a 4 is 5 over 6. So we said x was a Bernoulli random variable, so its expected value is just the probability of success, which is a 6th, and the variance of this random variable is just the two probabilities multiplied together. 1/6 times 5/6, which gives you 5 over 36. All right, let's now look at the binomial distribution. So the reason we learned about Bernoulli trials or Bernoulli random variables is that if you put lots of them together, they make up the binomial distribution. The binomial distribution helps us calculate the probability to get x successes from n independent Bernoulli trials. So we saw in the previous slide that rolling a die and letting x be the number of 4s was a Bernoulli random variable. The binomial distribution would arise if you rolled heaps and heaps of dice and you wanted to calculate the probability you get a certain number of 4s. So if x follows a binomial distribution, we write it like this. It has two parameters, n the number of trials, and p is the probability of success on each trial. So this is the formula to calculate the probability you get exactly x successes from n trials. So this here uses combinations, which is why we've learned it again this year. And again, p is the probability of success, 1 minus p, the probability of failure. And we also have some formula here for the expected value and variance. So let's learn this by going through an example. So let's say a company makes pens, notes 4% of all its pens are defective. If we randomly select 25 pens, what is the probability that exactly 5 are defective? So we'll start by letting x, our random variable, be the number of defective pens. So here x follows a binomial distribution. X is not a Bernoulli random variable. X can take values from 0 to 25 inclusive. But each time we pick a pen, that is a Bernoulli trial. Each pen on its own can either be defective or not defective. So to calculate this probability, we use the formula up here. So the probability that the number of defective pens is exactly 5. So it is n. N is the number of trials. So we've selected 25 pens, each of them like a trial, each time we select a pen, and we want exactly 5 successes. So then we multiply by the probability of success each time is 0.04. That's our p, and we want 5 successes. And then we want 20 times that we select a pen that is not defective. So 0.96 to the power of 20. So because each trial is independent here, and it's independent in this question because we randomly select the pens, we multiply the probabilities. This is the probability you get 5 defective pens and then 20 non-defective pens. But hang on a minute, there are heaps of different ways that you could get 5 defective pens from 25. You don't have to have the first 5 defective and the last 20 non-defective. You know, I could get the defective pens on the 1st, 3rd, 10th, 16th, 22nd trials, for example. So the total number of combinations, the total number of ways I can pick 5 defective pens from 25 is this number here, and that's why we multiply at the start. So putting this in our calculator, we get about 0.002, so it's very unlikely to happen. So the expected value of x is just the number of trials times the probability of success. So 0.04 is 1 over 25. So we expect that 1 out of every 25 pens is defective. That's what the expected value means. For this one, the variance would be n, which is 25, times 0.04, so that's the same as the expected value, except you then multiply by the probability of failure on each trial. Here, like picking a defective pen is like a success on each trial. And of course, that would just give you 0.96, and if you square root the variance, you would get the standard deviation. So again, what that means is if I perform this experiment many times, randomly select 25 pens many times, I would expect each time to only get 1 defective pen, but this is like the average distance from the mean. I'll usually get between 0 and 2 pens is basically what it's saying. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.